Thanks very much for the invitation. It's great to see so many former colleagues and friends in the audience. What I'm going to talk about is a quite specific application of very high, ultra-high field to a burning question in neuroscience, which is you could summarize by saying, where the heck are we anyway? Where are we in the cortex? Is there a good way of defining where we are, which is something we can discover in individual subjects and we can use to average across subjects. So, and I'm going to argue that the way we know where we are in the brain is through myeloarchitecture. And I'm going to go through these slides really fast because it's getting late in the day. So, what quantitative 70 MRI neuroimaging can now achieve? Structural images with isotropic voxels of 0.35 millimeters with T2 star images and 0.5 millimeter T1 images. And I want to stress the quantitative. I don't think we should be using images with an arbitrary intensity scale for science. We should be using images where we know what the intensity scale actually means. Because MRI is a quantitative method, there's no reason why we can't do that. And so our images, structural images show cortical layer structure. We can make quantitative maps which index myelin and iron content, MP2 region flash. And we can do in vivo cortical parcellation via myeloarchitecture. I'll show how we do that later. And then we can do functional images with 0.65 millimeter isotropic voxels showing layer-dependent activation, as Federico has just been showing us, actually, using either bold contrast or cerebral blood volume contrast. We're not down to 0.65 millimeters with cerebral blood volume contrast, but we are down to about a millimeter. And then we can do connectivity maps with 0.8 millimeter isotropic voxel showing detailed fiber crossing patterns. The point about this is that we are now in an era when we can identify structurally a neuronal substrate. We can identify its function at a submillimeter level, and we can identify its connectivity. This should provide us with a much stronger foundation for making mechanistic models of how the brain works in humans. Now, just to illustrate the point about T1 maps showing a very good indication of myelin, this is a T1 map obtained at 70 in vivo using MP-RAGE with 9 inversion times. And this is a cadaver brain stained for myelin. You see they're extremely similar. But oh, wait a minute. Now, this is a bit high resolution for an MRI scan, isn't it? I swapped the labels. But the point is very clear that every detail we can see in the T1 map reflects very precisely the details you see in the myelin stain. But we can go much further than that, and I'll explain how that works later in terms of quantification. Of course, in Leipzig, we've been able to do all the standard susceptibility-weighted imaging, and what's much better than susceptibility-weighted images, actual quantitative susceptibility mapping, because it doesn't have the non-local effects, and it actually gives you a number, which is very closely related to the density of iron. And then, of course, turbospin echo imaging, which is strongly T1 and proton density weighted, but not at all T2 weighted. Most people are unaware of that, but it's actually not T2 weighted, the way that most people do it. And then, of course, we can do diffusion imaging with looking at multiple components, but I haven't got time to talk about that. This is now quite an old image showing the quality that one get at in a T2 star weighted image, where you can see the terminal intracortical veins there running perpendicular to the cortical surface in beautiful detail. And of course, even more clearly in the phase map to the right. But and again, this is just things we've been doing. I'm just running through this quickly before I get to the main argument. We've been looking at the details of the Havana, which is a tiny part of the brain, but has a very powerful influence on the reward system. It acts as a brake on the reward system. It's very easily identifiable at 7 Tesla, hardly identifiable at all at any lower field strength. So this is work recently published by Barbara Strottman. And then, yes, returning to the quantitative susceptibility maps, this is work of Andreas Schaefer showing how nicely one can pick out all of the basal ganglia, and there's the subthalamic nucleus next to the substantia nigra, very nicely defined using this technique. And, of course, fMRI. This is work of Robin Heidemann, and when he was with us. And this is 0.65 millimeter isotropic voxels. This is a echoplanar image in which you can see the stria genari. And, of course, when we do functional, a flickering checkerboard stimulus, we see activity localized to the cortex. And that's a bit longer acquisition. But look at the Z-scores up here, 15 or so. So there's plenty of signal to noise, even for these tiny voxels. Speaking of doing functional studies, I just want to compare. This is a slide from Renzo Huber, who's in the audience here. He's been perfecting VASO, which measures cerebral blood volume. This is slab-selective VASO. It works extremely well at 7 Tesla. This is the visual stimulus. In the bold image, we see a high signal in the sulcus. This is the sulcus here. We see a big signal in the sulcus. We can't really see which bank of the sulcus this signal belongs to, because we know that the bold signal builds up at the surface of the brain. But in the VASO image here, we see the sulcus now again defined, and the maximum is on either side of the sulcus. Thank you very much. Good. Okay, so that's the point of doing VASO. It's spatially much more specific to the activation. And then, of course, we've been doing connectivity imaging at 800 microns resolution, where we see the tracks going right into the cortex. And then lovely depictions of the fiber crossings, even with a B factor of only 1,000. Yeah, this is just to give you an overall view. One more slide of this overall view. This is very recent work from Andreas Schaefer comparing brains of Alzheimer's patients in terms of their quantitative susceptibility map, showing that there's a high amount of iron in the cortex of these Alzheimer's patients as compared with a normal control here, age-matched control. We know about that they got Alzheimer's because these are PET scans which use a tracer for amyloid plaque. And this is a very exciting potential application for 7T in the future. To do all of these high-quality, very high-resolution images, it would be nice to eliminate the head motion, and we have developed an embedded optical tracking system, which is now the basis of a startup company. If you're interested in this, I can let you know more about it, but it's extremely precise, better than 20 microns spatial accuracy, and better than 20 milliseconds latency, and simple and inexpensive components. So, getting back to the main theme. Cortical and subcortical detail at 7 Tesla is a game changer for human systems neuroscience. One of the ways in which the game has to change is that there should be no more spatial smoothing into Montreal Neurological Institute's space. This actually creates a lot of false positives and prevents comparison of the spatial extent of the activation. With this kind of detail, we can directly associate neural substrate with function. we can get onto some empirically based modeling of cognitive processes. We can appropriately seed connectivity patterns. We can interpret cortical activity on a layer-dependent way. And I want to point out why we don't need spatial smoothing. We don't need it for signal to noise, because we have lots of signal to noise, as I showed just now. We don't need it for estimation of statistical significance, because we can now use much faster computers to use permutation methods. And we don't need it for averaging across subjects, which is how it's mainly being used, because we can now create native in vivo myelo-architectural cortical maps. These do as good a job as Brodmann maps, maybe better. And this has been work from our lab and Matt Glasser and David Van Essen in recent years, and a whole lot of papers that have just come out. But I have to say something about how we get these maps of myelo-architecture. We really needed to know what MRI parameter actually corresponded to myelin. And so we've done a series of studies in cadaver brain. This is a tissue block of primary visual cortex. That's a T2 star weighted image. You can see the stria of Gennari here and the white matter there. If we slice this up and stain it for myelin basic protein, we can see the myelin, the heavy band of myelin, the stria of Gennari. We can then stain it for iron, see that the myelin in the cortex corresponds to iron also. One of the very sweet techniques we've been able to use in Leipzig is a proton beam microscope, which gives us, for thin slices of brain tissue, it gives us quantitative measures of elementary composition. Iron is the easy one. Here's the basic idea. You have a beam of protons which interact with the inner shell electrons of each atom, and characteristic X-rays are given off as the electrons return to their shell. And so we'll have a spectrum which we can analyze. And so we can get maps of iron. This is primary visual cortex, as I showed before. But we can also look at other parts of the brain. This is the central sulcus and primary motor cortex, primary somatosensory cortex, showing correlation between iron and myelin in this part of the brain. It's interesting why there is so much iron associated with myelin. It turns out that iron is actually associated with the perikaryon of oligodendrocytes, which are, of course, making the myelin sheath. So iron is actually required for the onset of myelination. So they go hand in hand, but not exactly everywhere. Now, with a microscope which tells us how much there is of each element, how are we going to find myelin? We found that if we scan for phosphorus, this is a phosphorus map and this is a sulfur map, we can combine these with a bit of calibration to actually give us a myelin map, a quantitative map of myelin. You can't get this from a myelin-stained microscope section. Any kind of histology just gives you shadowgrams. This is an actual map of myelin density. And then we can then compare our maps of myelin and iron with the T1, the quantitative T1 image, quantitative T2 star images, and so forth. And we can then do a multivariate linear regression, where we find that there's extremely good regression, showing that the T1, or R1 in this case, 1 over T1, is actually very nicely linearly proportional to the amount of myelin, and is only weakly affected by the amount of iron. So when we talk about T1 maps, we are talking about a good quantitation of myelin. So, once we have such maps, then we can compare like with like. We can do fMRI using observable Mylo architecture. We can create native subject-specific cortical maps. I'll show those in a minute. And then use anatomically defined ROIs to average functional data across subjects. And no smoothing, a huge improvement in experimental power. The amplitude and the extent of functional activity acquire independent scientific meaning when we don't smooth. We can localize activation within specific cytoarchitecture or brain organelles, and do a better job of modeling. And this is some early work which is now published in Frontiers in Human Neuroscience 2 years ago, where we show that in vivo we can see the border between primary motor cortex and Brodmann area 3A, which is relatively lightly myelinated in this quantitative T1 map, coronal map of the brain through the central sulcus. And this matches up nicely with the myelin-stained section. Just to advertise a book which has just come out, Microstructural Parcellation of the Human Cerebral Cortex. There's about 10 chapters in there giving really the basis for how one does in vivo cortical parcellation. This is sold by Springer, and it's selling quite well already. This is an early map from our lab showing the intense myelination of primary motor and somatosensory cortices and A1, as Federico just referred to. This is a flattened version of it. This is a rather early attempt we made using equidistant contours to make these maps of the cortex, but equidistant contours are incorrect. Why are we so interested in myelin? One reason is that it gives us a native cortical map, but another reason is it's actually very interesting in its own right. Of course, axons can be myelinated or unmyelinated, and it's worth noting that the myelination of unmyelinated axons can be promoted by electrical activity in neighboring axons. So we have a bootstrapping process for the formation of cast-in-stone networks in the brain. Myelination has the following 5 relevant properties. It accelerates the propagation of action potentials by a factor of up to 100. It decreases the energy cost of transmission by orders of magnitude. It increases the physical robustness of axons. It reduces electrical crosstalk between axons and other nearby neurites. And it inhibits synaptic plasticity by inhibiting neurite growth. You can't make a new synapse on a myelinated axon. Now, this inhibition of cortical plasticity tells us that areas in the brain which are heavily myelinated are probably less plastic. And that tells us a great deal about how the brain is organized. This is an idea which has really never been yet explored. And it's available to us with MRI at high field. Just to point out that layering the cortex is now something we really need to be able to do. Now we have intracortical resolution on structural images. This is cadaver brain scanned at 70 microns. This is the central sulcus. Traditionally, the way that one made contours was either with equidistant contours or with solutions of the Laplace equation. This shows, Miriam Bennett implemented the solutions of the Laplace equation. It shows that the contours from such an implementation don't fit the layer structure of the cortex at all. It's a completely pointless way of doing it. In fact, what we've done is to actually mathematically formulate the Bock principle. Bock was a Dutch neuroanatomist published about 1929, in which we, using a level set approach to segmentation and formation of contours, we make sure that cortical segments keep their volume as you go around the curvature of the brain. When we do that, we get beautiful fit to the actual observable layers. Now, this is again the sphere of Gennari, and this is published by Miriam Bayonet in Your Image this year. Oops. So using these contouring techniques, we can now make maps of T1 across the cortex, which show no Ripley effect of the cortical folding, but show rather beautifully 3 different layers of the cortex, the map of myelination. So we can see primary motor cortex, Brodmann area 3B, Brodmann area 3A in between there. In deeper layers we see signs of the Brodmann areas 1 and 2, and many other cortical areas, including MT down here, just in a single subject. And this is based on 0.5 millimeter MP2 range data. We can also start to associate cytoarchitecture as known from the von Economo cytoarchitectural map with predictions of Mylo architecture, and we can use this to start to parcellate the brain in fine detail. Okay, I'm nearly finished. The opening window. 70 MRI is revealing fine structural details at 300 micron scale, functional activity at 650. In vivo Brodmann mapping can provide much more precise association of function with this neural substrate. We can get rid of obsolete analysis techniques which involve smoothing, and we should be getting rid of DTI for similar reasons. Using this level of detail, neuropsychological modeling of functional brain mechanisms can at last combine structure, function, and connectivity. We can distinguish cortical layer specific activity. We need new tools, and in Leipzig we've developed tools for analyzing unsmoothed fMRI data under the heading of Lipsia, and we have CBS tools which is extremely nice for doing this investigation of cortical layer structure. And of course one uses either DSI or spherical harmonic decomposition for tractography. Just 2 slides showing how much we've published on neuroscience at Leipzig in the last 2 years. It's really moving, this field, and thanks for your attention.